In a data frame, our measurements or measurement variables are typically organized in columns. What we do when we calculate like basic statistics as the mean or the standard deviation, we apply those calculations to each of the columns. And we calculate the value, like the mean, separately for each column as if the others were not there. So we look at columns independently. However, in machine learning, we are interested in whether there are any patterns that stem from relationships between columns. So it means it's a different type of data analysis where we take at least two columns into account and try to find pattern in the relationship between those two columns. So I'm going to demonstrate two such relationships. One is quantitative and the other is qualitative, but both done visually just by visual inspection, and we're in both cases using the scatter plot. To do this, we need to import two functions. From pandas, I import the read CSV, so to get our data if they are in comma-separated value format. And then for plotting, we use something matplotlib.pyplot. We import subplots to make our plots within JupyterLab. So to see some data, we import them using, of course, read CSV, which we have just defined. My data are in a folder which is called data, and the data file specifically called patients.csv. Then if we want to have a quick overview, we get the head function and we look at it and we can see that there's a number of rows for 7 columns. Not all columns are measurements, some are just categorization. Like you can see there's smoker and gender on the right hand side. And so the others are age, height, weight, systolic and diastolic blood pressure. Let us now pick 2 columns of this data frame and create a scatter plot. So we start by defining the axes. In a figure environment, we have a set of axes, and we do that using subplots. And in this coordinate system, we do a scatter plot, which needs 2 main arguments. The first is the data that go on the horizontal axis. So let's just pick one. Let's pick, say, the height. And on the vertical axis, which is the second argument, from that data frame, pick, say the weight, right? And this gives us a basic scatter plot with a semicolon. This additional output is suppressed. Now what we see here is the height horizontally against the weight and how it scatters or distributes in that area. The area, we could call it the space of states. All possible combinations of height and weight can be plotted in this area. And notably what we see in this one here is that the upper left corner here seems to be empty, so there are no points there. And similarly, we might suspect that in the lower right corner there are less points that you would expect if those data were distributed evenly. So for example, it looks very different if you plot the age against the weight. Then there's a different kind of distribution. If we just go back to the height, you can see, yes, notably this part where something is missing. So if we want to quantify that, we could use the correlation. And the correlation is the question, how close are these points to the main diagonal? So why diagonal? Well, diagonal is the extreme case of perfect correlation, in the sense that if you plot a data set against itself, like if you plot the weight against the weight, which are of course the same numbers in there, and then they will all lie along the main diagonal. If you know the correlation coefficient, there's also anti-correlation. Anti-correlation meaning that one data set is the same as the other data set, just multiplied with -1. So you can also realize that if you put on the vertical axis minus that numbers, then you will see perfect anti-correlation, which is this negatively sloped diagonal. So let's go back to the original and let's see. So perfect correlation looks like this. And what we now want to ask is whether height against weight is not perfectly correlated. Obviously, it's not on the main diagonal, but whether those points are more or less aligned along that main diagonal. So of course the easiest thing to do is to not guess it visually, but to have a plot included, to have a line included in that plot, and I'll just show you how you can do that. So we can include a line using plot on that same coordinate system, obviously, and the way to do a line with plot is to specify the coordinates of 2 points and then connect them with a straight line. So the x coordinates need to be followed by y coordinates, and we use a trick to do this. So the trick is to specify dots, 2 dots in the unit square. So from 0, 0 to 1, 1. First is x coordinates and second is y coordinates, and then use the function transaxis to transform this unit square to the current plot. So the current is within matplotlib can be identified as transaxis, but you need to say which coordinate system, and we have x dot. So if we use this piece of code, we can then have a straight line, which just happens to be the diagonal, using this unit square trick here and this transformation. And we can also have that colored in red, so the keyword C equal, and then if we put R in quotes, then we have that colored in red. And you can see it's not perfectly on the diagonal, but it seems to be aligned to a certain extent along that red line, which would make us suspect that there could be a certain degree of correlation, so correlation coefficient that is positive because the slope is positive, but is somewhere between 0 and 1. It will not be 0, it will not be 1, somewhere in between. Well, we don't do the quantification now. We just want to visually say that there are reasons to suspect from visual inspection that there is some correlation between height and weight in this case, which might be plausible if you think that larger people might be heavier in general. Right, let us now look at a qualitative feature. And to do so, I'll just copy that code and I'll show you an extra keyword argument. So that was our original scatter plot. And another keyword argument that we can use in addition to the color is S. And S for the size or the area of that dot that is plotted for each point. And to find out how it works, you just have to put in a number. So if you put in number 10, you can see those dots are fairly small. And now we play with that number, making it 100. Dots get bigger, making it 1000. Dots get even bigger, making it 10,000. Dots get very big. The axes don't scale automatically, so that's why it goes outside the range, but I don't worry about this at the moment. I want to point your attention to the fact that we have actually seen a very strange change in pattern. Can you see what we have now? Sort of one big blue area within that rectangle. But if we go to 10, we don't see that area. We see many dots, many individual dots. And somewhere in between, say like 800, we can see sort of different areas where the dots are connected. So there's an odd dot here, but these dots are all connected. And then there's connected dots up here in that upper right corner, one isolated, but notably there's this gap in between those two. Can you see that gap? So it makes us suspect that for a certain parameter of the plot, in this case s equal to 100, like which we just found by playing around with it, there is a suspicion that might tell us probably these data can actually be grouped into two subgroups. There's the one subgroup up here in the upper right corner and another subgroup in that lower left corner, and maybe these point to different features in the people on which they were measured. So what we can do is we can now try to make that more visible, what I've just tried to explain verbally, by using a straight line. Just take the code from before. So if I add the diagonal into this plot, of course we'll see diagonal, and that was what made us suspect some positive correlation. But that's not what we're interested in. We're now interested in that gap between those two. So how about making a line that tries to find that gap between those two areas that that are outlined by the overlapping blobs. So to have a line with negative slope, we have to have a decrease here. So if we go from 0 to 1, just the anti-diagonal, so to speak, and we plot that in, you can see that goes from top left to bottom right. And actually it's not such a bad guess. It's not so far away from the gap. And we can do a little bit better maybe. Let's try one or two approaches. So if that line was supposed to go through that gap here, that bottom right corner should be a little bit higher, right? Oh, we can do that because the bottom right corner is 0, which is here. And if we replace that with 0.2, that line comes a little bit up, and we can see, oh, it's doing much better. We still have one area cross, so if we increase it a little more, 0.24, you can see, oh, that fits just through that gap between the two main areas. What does it mean? We have found a line that helps us quantify by that slope of that negative slope of that line, that there is a way to distinguish between whether a dot is in the lower left category or in the upper right category, right? Some two subgroups that we have identified visually at a certain marker size, and now we have fitted, sort of manually fitted this line to separate those two. And if we express that technically, what we have done here is a manual way of doing unsupervised learning, unsupervised machine learning. Or if you like, clustering into two clusters. We have clustered those data into two clusters, one that can be defined as lying below that line and the other lying above that line, which has a slope that is specified up here. Our next step will be to understand, now we've seen how to find a relationship or a pattern in a plot where we have two data sets. And of course, the advantage of machine learning is that we can use those tricks both for correlations and for unsupervised learning on data frames that has as many columns as you like and not just two.